Hello, my dear students. This is your online English medium combined mathematics class. I'm Rajikam Ratna. Today we're going to start numbers and functions lesson. Okay, let's start from the beginning. Okay, let's start. Write down today new topic, numbers and functions. Write down new topic, numbers and functions. Numbers and functions. Okay. Now see this one. You know the things about numbers, no? You can count, no? You know how to count 1, 2, 3, 4, 5, 6, likewise, no? Then what's the end point? That can you count? What's the end point? That can you count? We can count up to 100. We can count up to 1000. We can count up to 10,000. What's the end point? Do you have any idea? We can count, but we can't imagine what's the end point. Okay? We can't imagine. Okay. Then when we count, we can count 1, 2, 3, 4, 5, 6 likewise. Then we use digits first. So when you consider about numbers, we have digits. Say 1, 2, 3, 4, 5, 6, 7, 8, 9. Then later it found about 0. Then 0, 1, 2, 3, 4 up to 9 we call digits. Okay. Then these are objects, no? Digits mean just objects. So likewise we have characters. In English we have A, B, C, last Z. Then we have 26 characters. And here we have 10 digits. So when you consider these digits, we can arrange them along a line. So you consider 1, 2, 1, 3, 4, 6, 1, 5, 6, 2. Likewise, 1, 0, and 1. These are we call numbers. These are digits and these are numbers. Then you can consider digits as number. Digits as a number. Usually we say that is a digit. But again we can say these are numbers. 1-digit number. Here 2-digit number. 3-digit number. Likewise you can create numbers. So numbers mean line arrangement. Okay. When you consider digits, we can arrange along a line, then we can create a number. Line arrangements. We call they are permutations. Arrangement means permutations. Okay. Then we need to think about that permutations first. We have to think about that permutation first. Then we can create numbers. Okay. Okay. Now you identify basic concept of mathematics. Basic concept of mathematics is about a number. Okay. Basic concept of mathematics is about number. So that has made using digits. Okay. Then we have 10 digits. By arranging them along a line, we can make a number. Then using these numbers, we can do many things. That's the basic concept of mathematics. So by these numbers, so we use these numbers for counting purposes first. Okay? For counting purposes, we use numbers first. Those are we call natural numbers. So when you consider 1, 2, 3, 4, Likewise, this set we call natural set. Natural set. We use them for counting purposes. So here we don't have any endpoint, but we say that end at infinity. That ends at infinity. Then infinity we can't define infinity, but we can say it is a very large number. That depends. Okay, so that depends. Then infinity very large number, its value can't be defined. Then you identify infinity is a very large number. Then this set we call natural set. Natural set. So thereafter we introduce two operations. One is addition. The other one is multiplication. Multiplication. So to define this addition, we have created integer set. Integer set. So when you consider 1 plus 2, we can say 3, we know that number using natural set, no? So when you consider 2 minus 1, again we can define that 1. When you consider 3 minus 5, then using natural numbers we can't define. Then we have to make another new number set. Then minus 2, then negative numbers appear. Therefore, minus infinity, minus 1, 0, 1, up to plus infinity numbers has made. That is we call integers. Integers. Then minus infinity to plus infinity, all cardinal numbers we call natural integer set. Therefore, when you consider this integer set, then natural set also subset of that integer, no? Subset of integer. Then thereafter this part positive integer and this part negative integer, and with 0 this part we call non-negative integers, and here with this part we call non-positive integers. Here positive integers, negative integers, here non-positive, non-negative integers with 0, and here this one we call non-positive integers. Likewise, you can classify further numbers. Okay. Then thereafter, multiplication, we have 2 times 3, we can define this 6. 3 times 5, we can define this 15. Using integers, we can define. Then 4 divided by 2, we can define 2. But 1/3, we can't define using integers, no? We can't define those using integers. Therefore, to define this one, we have to get another new number set. We call rational numbers. Rational numbers. Then we have rational set. Then number like p divided by q, we call rational numbers. And you have to remember here p integer, q integer. Therefore, half we call rational number. This must be integer, this must be integer, and this not contain common multiple. That not contain common multiple. Then when you consider 2 divided by 4, 2 divided by 4, it is like p divided by q. But you can see here common multiple, no? You can see here common multiple. So if we have common multiple, we don't say that is directly rational number. Then these two are same, but this is rational, but this is not rational number. It is like p divided by q or integers. But if you have common multiple, we don't say that is rational. But cancelling that common multiple, we can rationalize it. So by cancelling, you can go to reverse. Then half is rational. That process we call rationalization. Rationalization. Okay, that is rational number. Then we have initial we have number set, natural set. Natural set. Thereafter we have introduced integer set. Integer set. Thereafter we had to introduce rational set. We can define by q hat. That is we call rational set. Then again we have irrational numbers like square root 2, square root 3. We can't write this one as fractional value like mixed fraction or whatever. P divided by q pattern we can't write. Then root 3 and especially pi, e. These numbers we call irrational. Irrational numbers. So here do two different things. One is rational, the other one is irrational. There's one specialty. So when you consider rational number and decimal format of that, then decimal format can be finite decimals for rational, but for here this one, that is surely infinite decimals. And here this can contain finite decimals and as well as infinite decimals, both possible here. But for this one, only infinite decimals. So here finite decimal, and I told you it can get infinite decimals, no? So if it has infinite decimal, then it has nice pattern. We call recurring pattern. For rational, it has nice pattern for infinite decimals. But for irrational, we don't have any nice pattern, but decimals are infinite. That's the specialty. Then thereafter, we had to introduce irrational set. Then that away from rational one, then let's say take this one, irrational set. Then all together we say irrational, rational, all together we say this part real set. Real set. Then here irrational and then rational union we call real set. Then and always we done up to that. Okay, we use rational numbers, we use irrational numbers, natural numbers and integers, so on. But further we have further numbers. So with the operation we have to introduce new numbers. With the operation we have to introduce new numbers. So natural numbers we use for counting purposes. Thereafter with algebraic operation we have to introduce integer set. Again with algebraic operations we have to introduce rational set, and likewise we have to introduce irrational set. Then union of these two we say real set. Then further we have further classifications here that belongs to imaginary numbers and complex numbers. We have done small little things about complex numbers and imaginary numbers. Then those are the number set. Those are the number set. Okay. Then you have analyzed a lot of things under numbers, but we have to go special points on these numbers. Like rationalization of denominators. You have done little things, but we have to do more practices. Rationalization of denominator. And again we have, I told you, for rational numbers, we have infinite decimals. Sometimes it can have infinite decimals. So for infinite decimals, recurring decimals, we have to express like fraction. Likewise, those conversion we have to do, we have to practice that. And again, with irrational numbers, we have to practice contradiction method. That's new method for you. Contradiction method to prove square root is irrational number. It's an irrational number. Okay. Those are the things that what we need to discuss under number lesson. Number lesson. Okay. Okay. Just write down. Basic concept of mathematics. Basic concept of mathematics. Basic concept of mathematics is about a number. Basic concept of mathematics is about a number. There are 10 digits. There are 10 digits. There are 10 digits. Okay, within curly bracket write down. Within curly bracket, comma separator 0, 1, 2, 3, 4 up to 9. Within curly bracket write it. Curly bracket 0, comma separator 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, just write further. By arranging those digits, along a line, along a line, along a line, along a line, further numbers are made. Further numbers are made. Further numbers are made. Further numbers are made. Okay, just write few examples. 1, 2, 3, 4, 5, 6, 2, 1, 0, 1, 1, 5, 0, 1, here you say this is not a number. Here these are numbers. Their specialty, we can't put 0 at the beginning. Zero at the beginning. So if you put 0 at the beginning, we don't say that it's a number. Okay? 1 0 is a number, but 0 1 is not a number. That's very important. Okay? 0 0 1 not a number, but we write them. But we can't identify them as a number. Okay? Okay, write them. Okay, then here these are line arrangements. So you consider arrangements. This is we call permutations. Another word, permutation. So later we have lesson permutation and combination, but just identify permutation in arrangement. So you consider here 3 students that need to arrange along a line. Here line arrangement. And if you consider a circular table here, so we can arrange along a circular arrangement. We have 2 type arrangements, line arrangement and circular arrangement. But when creating numbers, we use only line arrangements. We can create only line arrangement. Then we use this. Put that note. So arrangement here, there are 2 types, line arrangement, circular arrangements. Then here these are objects, can be students, can be numbers, can be letters. Okay, we can arrange them, but only line arrangement we consider as a number. Okay. Arrangements, permutation. Here line arrangement, here circular arrangement. We have 2 different arrangement type. Don't worry about things, but just I introduce that. Okay. Now you write this say. Initially, numbers are used for counting purposes. Initially, numbers are used for counting purposes. And thereafter, with the algebraic operations, further numbers are evaluated. Further numbers are evaluated. Further numbers are evaluated. Further numbers are evaluated. Therefore, numbers can be classified, therefore numbers can be classified, therefore numbers can be classified as the given below, as the given below. Okay, now you write with me, first one, natural numbers. Write with me. Here we denote by this type of n letter, natural number. So under that write down, here within curly bracket 1, 2, 3 up to infinity. This we call infinity. Within curly bracket, because this is a set, comma separated one. You have to put at least 3 dots here, otherwise it is wrong. You have to put at least 3 dots. So it is a series. It is a sequence. Therefore, we have to put at least 3 dots here. Under that write down, all cardinal numbers from 1 to infinity, all cardinal numbers from 1 to infinity, all cardinal numbers from 1 to infinity are belongs to natural set, all cardinal numbers from 1 to infinity are belongs to natural set, Here infinity, we denote by this, not this one, this is alpha, infinity, like this. Infinity is a very large number. Infinity is a very large number. And it is a concept, but the value can't be defined. Infinity is a very large number and it is a concept, but the value can't be defined. Okay. Then identify infinity is a very large number, but its value cannot be defined. Okay. Now you consider here, if you consider 1, 10, if we add 1, we know that is 11. No? If you know 1000, 1000 plus 1, we say 1001. So if you consider 100,000 plus 1, 100,000 plus 100,001. No? So tell me, what is infinity plus 1? What is infinity plus 1? It is another infinity. Then infinity means very large value, no? Infinity means very large value. So when we add 1, then again that will be very large, no? Then you say that also infinity. But that infinity is somewhat greater than previous infinity, no? Therefore you have to write little like this. Okay? Say infinity. Yeah? Anyway, identify infinity plus 1, infinity. Then infinity plus 2, what will be? Again infinity. Infinity minus 1, again infinity. So infinity minus 0, infinity. Infinity plus 0, infinity. Then infinity plus 100, infinity. No? Then tell me, infinity minus infinity. Infinity minus infinity. Okay, let's see. You put this infinity other side, then infinity minus infinity 1, no? You put this infinity other side, then infinity minus 0. Do we have anything like minus 0? No, it is conflicted. So if you put this on the other side, then infinity minus infinity, it is 2. So if you put this on the other side, infinity minus infinity, now minus 1. If you put this on the other side, infinity minus infinity, 100. Then there are a lot of answers, no? Lot of answers. Then it is very doubtful. Then further onwards, you say infinity minus infinity, undefined. Undefined. Don't try to define it. You say it is undefined. Then infinity minus infinity, undefined thing. Then likewise in mathematics, we have few different undefined relations. We have few different undefined relations. So here are they. Infinity minus infinity, we can't say the answer. We say undefined. Then likewise, 0 times infinity, we say another undefined relation. Later I will discuss how it is happen. Then 0 divided by 0, undefined relation. Infinity divided by infinity, undefined relation. I'll tell how it is happen. 0 to the power 0, undefined relation. Undefined relations. Relation. This is an undefined relation in mathematics. We don't try to justify them. Okay? We don't try to further analyze them. Okay. Now these are undefined relations that comes with infinity and 0. That's why 0, infinity, special numbers. That's why we introduce 0 and infinity as very special number. Okay? Okay, write down. In mathematics, there are undefined relations. There are undefined relations. In mathematics, there are undefined relations. Okay, write them. Infinity minus infinity, 0 times infinity, 0 by 0, infinity by infinity, 0 to the power 0. These are undefined relations. Just write. So all are deals with infinity and 0, no? All are deals with infinity and 0. Then infinity and 0, very critical thing. Okay, just identify. So if you see this type of relation, you can stop there with undefined relation. Okay, now let's see how infinity appear. Let's see how infinity appear and how 0 appear. Then you consider 1 over 1. We say 1 over 2, we say 0.5. 1 over 10, we say 0.1. 1 over 100, we say 0.01. 1 over 1000, 0.001. Then it goes on. Then let's put 1 over infinity. Let's see what will happen. So let's take real number line. You mark 0 here, you mark 1 here. So here 1, here 0.5 at the midpoint. 0.1 divided into 10 sections, then small part will be 0.1. Then 1 over 100 is too close to 0. 1 over 1000, too close to 0, no? So when you increase denominator value, that tends towards 0, no? That tends towards 0. then definitely that won't exceed 0. That can't go beyond 0 there. But that can comes towards 0. Did you get it? Then here 1 over 1000, 0.01, 1 over 10,000, 0.0001, 1 over 100,000, 0.00, so on. No? So it comes towards 0. Therefore, when it goes to infinity in denominator, you say that is tends towards 0. This notation we say tends towards 1 over infinity, not exactly 0, so close to 0, then that tends towards 0. That tends towards 0. That's how 0 and infinity appear. Okay, this is not equal sign, it represents tendency. Therefore, you remember 1 over infinity that tends to 0. 1 over minus infinity also same. You say that tends to 0. 1 over minus infinity. So here 1 over infinity that come from right hand side this way. So if you consider 1 over minus 1, 1 over minus 2, minus 0.5, 1 over minus 100, minus 0.1 over 10, 1. 1 over 100 minus 0.01. So 1 over 1000 minus 0.001. Therefore, 1 over minus infinity, that tendency towards 0 again. Okay, so here minus 1, then minus 0.5, minus 0.1, and it goes so on. It tendency towards 0, but that can't exceed 0. No? So we don't have anything like minus 0 plus 0, but we have minus infinity and plus infinity. Okay, we have minus infinity and plus infinity. Then 1 over infinity plus infinity, you say that tends to 0. Then 1 over minus infinity, you say that tends to 0 again. Here this one that come from right hand side, this say, no? Right hand side, that belongs to positive. Therefore, you can represent that one by 0 plus here. 0 plus. That mentioning that comes from positive region. Then 1 over minus infinity, here it comes towards 0 left hand side. Then you say that is 0 minus. Okay, that represent the variation positive region here and variation here negative region. That's important thing. Okay, now with this one, then 1 over plus or minus infinity, then 1 over plus or minus infinity, anyway that tendency towards 0. Tendency towards 0. Then if you cross multiply, then 1 over 0, that tendency towards plus or minus infinity. Plus or minus infinity. Again, important relation. That can be plus infinity, that can be minus infinity. So this happened, y equal 1 over x, take this one. So if you sketch this graph, put values here, x equal 1, y value 1, x equal 2, y value half, x equal 10, y value 0.1, x equal half, y value 2, x equal 1 over 100, y value 100. Then the graph is like this. Don't worry about the pattern, but you identify it can happen like this pattern. So for negative value, it graph like this. For positive value, graph like this. Therefore, when it goes to 0 plus side, it is plus infinity. When it goes to 0 minus side, it goes to minus infinity. Okay. Therefore, here you can further classify 1 over 0 plus side. 1 over 0 plus side, here tendency plus infinity, 1 over 0 minus side, then tendency minus infinity. Minus infinity, no? Just identify there are a lot of things under infinity and 0, but just this is enough. This is enough. Don't worry about the things. I just explain how infinity happen and how 0 come. Okay, just note them. Okay, you just identify about these notations, but no need to remember for now. Just identify, yeah, that's enough, because later we will discuss under limits this arrow, then 1 over infinity goes to 0, like those things we gonna analyze later. Okay. Now write with me. Write with me. Infinity plus 0, infinity. Infinity plus 1, infinity. Infinity plus 10, infinity. Infinity plus 100, infinity. Infinity minus 1, infinity. Infinity plus infinity, infinity. Therefore, infinity minus infinity like 0, infinity minus infinity like 1, or infinity minus infinity like minus 1. Therefore, infinity minus infinity 10, or infinity minus 10, and so on. Therefore, you say infinity minus infinity undefined. That's why we say infinity minus infinity is undefined. These are okay. Infinity plus 0, infinity. Infinity plus 100, infinity. Infinity plus infinity, infinity. These are okay. Yeah? We can define them. We can define this infinity. We don't know what is the value of infinity, but we can define that. So anyway, finally you say infinity minus infinity is undefined. Infinity minus infinity is undefined. Okay. Okay, now you come to this set 2. Set 2. See this one? First see this one. First see. 1 times 0, 0. 2 times 0, 0. 100 times 0, 0. 1000 times 0, 0. Therefore, number times 0, 0. No? Then when you consider this number like infinity, infinity times 0, now it appear like 0. No? So according to this pattern, infinity times 0 appear like 0. Now you consider 1 times infinity, infinity. 2 times infinity, infinity. 10 times infinity, infinity. Then 1000 times infinity, infinity. Therefore, according to that number times infinity, now it infinity. Therefore, you take number like 0, 0 times infinity, according to this pattern, is look like infinite. No? 1 times infinity, infinity, 2 times infinity, infinity, 10 times infinity, infinity, 1000 times infinity, infinity, then number times infinity like look like infinity. Then if you consider 0 times infinity, it look like infinity. But previously, according to this pattern, infinity times 0 look like 0. Then now it is conflicted, no? Conflicted. That's why we say, because of these two, we say infinity times 0 is undefined. That's why we say infinity times 0 undefined. Okay, just write it. No need to prove them, but you think and remember 0 times infinity is undefined. According to one pattern, it's look like 0, and with this pattern, it look like infinity. That's why we say 0 times infinity is undefined. 0 times infinity is undefined. Okay. Now let's move a little further. Now we know infinity times 0 undefined. Infinity times 0 undefined. No? And further we know 1 over infinity that tends towards 0, 1 over 0 that tends towards infinity. That can be plus infinity, minus infinity, both okay. But here 0. Here for plus or minus infinity that tends towards 0, and here for plus or minus infinity. Okay. Now you come to infinity divide by infinity and 0 divide by 0 relation. Now when you take this according to general algebra, infinity times 1 over infinity, no? Infinity divide by infinity times 1 over infinity. Don't cancel. So you can't say that is 1. You can't say this is 1. Because here this infinity and here this infinity can be different infinities. No? Now 1 over infinity that tends towards 0. No? Then you can say this is 0. Then infinity times 0 now appear. Then 1 over infinity that tends towards 0. Now we know 0 times infinity undefined. No? Therefore 0 times infinity happen with infinity by infinity. Therefore you say this one undefined, then here also undefined. Similar here, 0 times 1 over 0. Then here 1 over 0, that infinity. Therefore this is undefined, here also undefined. Okay. Then 0 times infinity, 0 divided by 0 and infinity divided by infinity, all of them are like same, look like same. Okay. Therefore you say 0 times infinity, infinity divided by infinity, 0 divided by 0, they are undefined relations. Better write them as well. Okay. Now here these are very rare cases under numbers. Those are not that much famous, not happen frequently, that happen very rarely, but you have to remember them. So in O levels you haven't discussed these things, but O levels also and A levels also we have to not frequently happen this one, but we have to remember. Okay, now let's move a little further. Okay, now that's all about infinity and natural numbers. Now let's move further. So write with me, integers. Integers we define by z like this. Integers, write this set minus infinity, minus 2, minus 1, 0, 1, 2, infinity. Here this is integer set. Then for this part we say positive integers. Positive integers. For this part we say negative integers. And for this part we say positive integer with 0, no? Positive integers with 0. We call non-negative integers. And here this part we say negative integers with 0. We call non-positive integers. Non-positive integers. Yeah, non-positive integers is at 0 minus. You have to remember these notations. Negative integers, non-negative integers, positive integers, non-positive integers. Then altogether integer set. And this is natural set. Okay. Now with star mark write down, all cardinal numbers from minus infinity to plus infinity, all cardinal numbers from minus infinity to plus infinity, all cardinal numbers from minus infinity to plus infinity R belongs to integer set. R belongs to integer set. Next star mark. Next star mark. The natural set is a subset of integers. The natural set is a subset of integers. Natural set is a subset of integers. So here we can define, write this way, denote this way. Here natural set, here integers now, here subset. Natural set is a subset of integers. Smaller one goes to here, left side, okay? Okay. Now you come to here, rational numbers. Rational numbers, we denote by here this say q with hat. Rational numbers. We have to practice this one. Here there's definition for rational. So here we write p divided by q pattern, where pq integers, where pq element of integers and denominator q that not equal 0, and here pq, it says that pq doesn't have any common multiple. This notation idea, pq doesn't have any common multiple. That's why I told you 1 over 2 rational, but 2 over 4 not rational directly, but we can rationalize. This mentioning p and q don't have any common multiple. Okay. Okay, write that definition. So these three conditions must be satisfied. Those three conditions must be satisfied to be a rational number. So we have to practice this part. You have different question type. Okay. Now you write examples. By the side, write down examples. 1 over 2. Write this way. 1 over 2 equals 0.5. 1 over 4, 0.25. 3 over 5, 0.6. 1/3, 0.3 dot. Here 0.333. Put at least 3 dots here. Then 0.3 dot, recurring decimal. Then 67 divided by 99. 0.676767. It goes on 0.67 bar. Then 2 decimals are repeated. Then when you check them, so like p divided by q, pq integers and denominator not equal 0, it doesn't contain common multiple, rational. Okay, it is rational. Then here p divided by q pattern, pq integers, denominator not equal 0, and p and q doesn't have any common multiple, no, rational. Then all are same, all are rational numbers, no? Then all are rational numbers. Then very special thing, 1 over 2, 2 divided by 4, here rational, not rational directly. Here 2 times 1, 2 times 2, here we have common multiple. Because of that, it is not rational, but can rationalize. By cancelling, you can rationalize it. Then we can rationalize. Okay. Better write that examples. Okay. Now with star mark write down. When considering decimal form, when considering the decimal form of a rational number, decimals can be finite, or infinite. Decimals can be finite or infinite. If the decimals are infinite, they are recurring decimals. They are recurring decimals. They are recurring decimals. That is the major property of a rational number. That is the major property of a rational number. Okay. Now under that, you put this topic under rational part. Before that, put star mark and write down. Put star mark and write down. The natural set and the integer set. The natural set and the integer set are subset of rational numbers. Are subset of rational numbers. Here natural, here integer, and here rational. Okay. Put that Venn diagram. Natural set, integer set, rational set. Here small one natural, then integer, then rational. Therefore, in other words, integers we can say rational, no? Natural we can say rational. No issue. When you consider integer like 2, you can write 2 divided by 1, like p divided by q, q integers, q not equal to 0, and so on. No? That's why I told you all integers are rational. Okay. Now next special subtopic, recurring decimals to fraction. Special subtopic, recurring decimals to fraction. Recurring decimals to fraction. Okay. Now this is really important part because for your first term test, there will be recurring decimal to fraction question or 2-3 questions. Okay. Then, but not in A levels, okay, for your first term test, recurring decimal to fraction. Let's see how we do that. You consider this first 0.1111, here it goes up to infinity. Therefore, here we call recurrent decimal. So, one decimal is repeated, no? One decimal is repeated. So, I'm going to take this one as x first. You say this is 1. So, one decimal is repeated, no? So, if I multiply this one by 10, let's see what will happen. 10x. Before that, let's write this one 0.1 dot. Here compressed format, that dot represent it is recurring. 1 is recurring. Say 2. Then I'm going to multiply here 1 by 10 because one decimal is repeated, no? Then 10x equal 10 times 0.1111, it goes on. So if I multiply by 10, we can put one decimal the other side, no? Left side. 1.111, it goes on. So previously it has infinite decimals, no? Infinite decimals. So if I multiply by 10, now here decimals infinity minus 1. No? So this is infinity, decimals infinity, then here decimals infinity minus 1. But we know infinity minus 1, infinity, no? Then here you can say 1.1 dot again. Here 1 dot, that is 10x. So we're going to find x. So when you subtract, let's say 3 here, 3 minus 2, then 10x minus x equal 1.1 dot minus 0.1 dot. Here 1.1 dot minus 0.1. Then 9x equal, here decimals you can cancel, then we get 1, then x 1 over 9. Then 0.1111 thing you can write 1 over 9. 1 over 9. So if you convert this into decimal format, definitely you get 0.1111 thing. Then here the way of converting recurring decimals to fraction or recurring decimals to rational number. No? This is fraction, or you can say rational. No? Then that's how we proceed it. Okay, do that example. Okay, then you try 0.2222. You try this one. I'll give you 1 minute. Zero point 2222 up to infinity decimals. Then similar procedure, we get 2 divided by 9. No? 2 divided by 9. Oh, on the other hand, 0.1 dot mean 1 over 9. No? Then 0.2 dot mean 2 over 9. No? 0.3 dot mean 3 over 9. Then 0.1, 1 over 9, 1 dot. 0.2 dot 2 over 9, 0.3 dot 3 over 9, 1/3, 0.4 dot 4 over 9, then it goes on 0.8 dot 8 over 9, then 0.9 dot, this is really important, 9 divided by 9, 1, then 0.9 dot mean 1. 0.9 dot mean 1. Okay, 1 0.9 dot. 0.9 dot means 0.9999999 so on, infinite decimals. Then we can say that is 1. Okay, better note them. This is fraction 3/9. This is rational, 1/3 rational. No? So here you can write directly. Need to start with 0 point recurring decimal part. Okay, we can write this one directly, 0 point then recurring decimals. Not all the others. Huh? That must be 0 point. That must be start with first decimal repeating. Okay. Now see this example. 1.555, here this thing. Take 1. 1.5 dot. Take 2. 1 multiplied by 10 because one decimal is repeated. Then 10x equal 10 times 1.555 goes on. Then 15.555, you have to put at least 3 dots. Without dots it is wrong. 5 dot. Yes, say 3. Now 3 minus 2. 10x minus x. 15.5 dot minus 1.5 dot. 1.5 dot. Then here 9x. Yeah, decimals cancel. We get 14. X equals 14 divided by 9. Now here the fraction. Recurring decimals has converted to fraction. No? Okay, do that example. First you analyze the things properly, then you do alone. No? First analyze the things properly, then you do alone. Okay, you try 5.4 dot. Okay, you try soon. 5.4 dot. That is 49 over 9. 49 over 9, no? Okay, you try this. 0.41111, so on. Think and do. So our procedure first, we're trying to remove recurring decimals part, no? We're trying to remove recurring decimal part. That's the procedure. Think and do. First you multiply by 10, get 4 left side, then 4.1 dot. Thereafter we can remove this one. Then you multiply again by 10, then 41.1 dot. Then subtract, then 100x minus 10x, here 90x. Here 90x. The other side 41 minus 4, 37. Then 37 divided by 90. 37 divided by 90. You try to make first value left side, then right side decimals must be repeated. Here you have to put this 4 the other side. That's why I multiply by 4 first. Thereafter from here decimals are repeated. Then repeated decimal, one decimal you can put left side by multiplying 10. Thereafter here and here decimals are repeated. So when you subtracted that, then you can remove repeated decimal, no? That's the procedure. Okay, you try. Okay, you try this one. Do alone. Here further we can simplify a little. You can divide by 2, no? 106 45, no? This is fraction, this is rational. So if you have to express like rational number, then you have to go here. Okay, then one decimal repeated thing, we can do that way, no? So likewise, 2 decimals repeated, 3 decimals repeated, 4 decimals repeated, we can go so on. So you take this example again. X equals 0.25, 25, 25 and so on. Here 0.25 bar, no? Take here 1, take here 2. Then there are 2 decimals are repeated, no? 2 decimals are repeated. So if 1 decimal is repeated, you have to multiply by 10. Then if 2 decimals are repeated, then multiply by 100, no? Multiply by 100. Okay. 1 times 100. Then 100 x equal 100 times 0.25, 25, 25 so on. Then 25.25, 25, 25 so on. Then 25.25 bar 3. Now subtract 3 minus 2, 100x minus x, 25.25 bar, 0.25 bar. Then 25, 99x, x equals 25 divided by 99. No? 25 divided by 99 is the fraction. That's how we convert it. Okay, do it. Okay, then you do that. 0.373737. Okay, take time. Thirty-seven divided by 99, no? Okay. Then when you see that one very carefully, 0.373737, then 37 come to here, then divide by 99, no? Then when you see that one very carefully, you can get the pattern 0.2523 bar. Here 23 divided by 99, that's it. 0.41 bar. 41 divided by 99, no? 0.15 bar. 15 divided by 99. Further we can simplify. 5 divided by 33, no? Then 0.16 bar. 16 divided by 99. Okay. Then remember, that must start with 0. If we have 1 here, we can't write. Huh? Here 0, that must be 0. Thereafter, from the first decimal, it must be repeated. From the first decimal, it must be repeated. Otherwise, we can't write. Then we can write this one directly with that two condition. Write them. Okay, now let's develop this pattern. Let's develop this logic. Then 0.7.7/9, 0.15 bar, you say 15/99. Then 0.135 bar, you say 135 divided by 999. 0.3759 bar, you say 0.3759 divided by 9999. No? So here one decimal repeated, two decimal repeated, three decimals, four decimals repeated, so on. Then further we can write 0.14325. Instead of bar, you can put starting dot, end dot here. It is that represent also recurrent. Then here 14325 99999. Here 1 2 3 4 1 2 3 4 1 2 3 4 5 9 99999. Okay. Okay. Note it. Now you know the pattern. You know the pattern. Previously we done the procedure. Now we analyze the pattern. Okay. Now see this. 0.1.3 dot divide by 5.4 dot. 1.3 dot divide by 5.4 dot. Then here you write 1 plus 3 over 9, 1 plus recurring decimal. No? Then let's do this, say 1 plus 0.3 dot. Here 5 plus 0.4 dot. No? Without dot is wrong. Don't forget to put dot. Here 3 over 9, 4 over 9. Then both upstairs, downstairs, you multiply by 9. Here 9 and here 3. Here 5 times 9 and here plus 4. 12, 49. Then here the rational form 12 over 49. No? 12 over 49. Okay, do it. Okay, you try this 12.3 dot minus 1.6 dot. Okay, you try it. I need simplest form. I need rational form. Twelve plus 3 over 9. If you can write directly, just write, but without any error. 1 plus 6 over 9. Here there will be minus outside. Then each term multiply by 9. 12 times 9 plus 3. 9 plus 6. Here you can see common multiple 3, no? Then better to cancel it. So previously also we can do that. Here cancel 3 and here 3, 2, 3. Cancel all common 3. Then 12 times 3, 37. 3 plus 2, 5. Minus 37 or 5 will be the simplest form. Okay, now here 0.1 mean 1 over 10, no? 0.1 mean 1 over 10. 0.1 dot mean 1 over 9. Then here, that's the important thing about dot, recurring part. Then you better rewrite that. Better rewrite. 0.1 mean 1 over 10, 0.1 dot mean 1 over 9. 1 over 9. Okay, by the side again write 0.37, 37 over 100, 0.37 bar, 37 over 99. 37 over 99, no? Okay, then you have to write all clearly and logically, both. Okay, here without dot, it is two different idea. Okay, with dot and without dot, two different idea. Then analyze it and take it properly. So up to now, we discussed the things about numbers. Then number mean that's the basic concept, that's the base of mathematics. Okay, then by that number we can develop many things. The numbers are the major thing under mathematics. Okay, then we have classified natural numbers, integers, rational numbers. Then thereafter we discuss about how to convert recurring decimals to fraction. So in rational number we have property that can be finite decimals or that can be infinite decimals. So decimals are infinite, we say that is surely rational with recurring pattern. Okay, infinite decimals with recurring pattern, that is rational. Then finite decimals also rational. But there is something that is recurring infinite decimals without recurring pattern. There can be infinite decimals without any pattern. Then they are not rational. Then surely they are the other thing, irrational, no? Okay. Then that's the way of identifying rational and irrational numbers. For rational numbers, decimals can be finite or infinite. If it is infinite, it has pattern. For irrational number, decimals are infinite without any pattern. Okay. Then these are the things about just numbers up to rational part. Okay, let's have a small interval. Okay, let's start again. Let's start again. Now, let's identify all the other numbers patterns, then we can do further more questions. Okay, write down irrational numbers. Irrational numbers. Irrational numbers. So we denote by I. Here irrational numbers. Irrational numbers. Okay. Now here irrational mean not rational, but that belongs to real. Okay. Irrational numbers are not rational, but that belongs to real. The specialty of irrational numbers, decimal format, infinite decimals, without recurring pattern, without any recurring pattern. So I here, it can't write P divided by Q pattern. It can't write P divided by Q pattern with PQ integers and Q not equal 0 and P and Q doesn't have any common multiple. With this condition, we can't write in the form P divided by Q. So as an example, root 2, root 3, root 5, then pi, e, these are irrational numbers. Then these two are very important number, pi and e, irrational numbers. Still this pi, value of pi and value of e still finding. Then we cannot write in the form x divided by p divided by q format. That is irrational. Okay. Okay, just write there. A number which cannot be expressed in the form p divided by q. Which cannot be expressed in the form p divided by q. With the conditions, write these three conditions: p, q, element of integers, q not equal 0, and here we say p and q doesn't have any common multiple. Okay. Write these three conditions. So we cannot express. Previously we can express, now here we cannot express. Then under that, better write irrational set here. Root 2, root 3, root 5, pi, e, put some dots. Here irrational set. Okay. Now you consider here pi. I'm telling here pi irrational number. Now 22 divided by 7. Is this rational or irrational? Now it is like p divided by q and q not equal 0, and here numerator denominator doesn't contain any common multiple. No? Now this is rational. No? Then 22 over 7 I'm telling we can consider as rational, but pi I am telling it is irrational. Pi irrational, but 22 over 7 rational. So now here somewhat confliction here. No? So which one is the correct one? So I'm telling pi is irrational. 2 and 2 over 7 rational. Which one is the correct? Both correct. Huh? Both correct. The thing is pi approximately equal to 2 and 2 over 7. They're not exactly equal. Then 22 over 7 rational, no issue. Pi irrational. Pi irrational. Then just approximate value is 22 over 7. Still finding this. Okay, that's the thing. Okay, with star mark write down. Pi is an irrational number. Pi is an irrational number. 22 over 7 is a rational number. 22 over 7 is a rational number. Pi irrational number. 22 over 7 is a rational number. But pi approximately equal to 22 over 7. Here pi approximately equal to 22 over 7. When you are doing sums, we take pi equal to 22 over 7, but that is not equal, that is approximately equal. Okay. Okay, then here also we have do few questions, but later we will do that. Huh? So let's complete all the theory part. Now you write real numbers. Here real set. Real set, rational, irrational union, we say real. Rational, union, irrational. Okay. Rational, union, irrational. Just write here. The union of rational and irrational set. The union of rational and irrational set is the real set. Is the real set. The union of rational and irrational set is the real set. Therefore, natural numbers, integers, rational numbers, and irrational numbers. Natural numbers, integers, rational numbers, and irrational numbers are subset of real numbers. Are subset of real numbers. All these real numbers can be represented geometrically. All these real numbers can be represented geometrically. All these real numbers can be represented geometrically by a point on the real axis. By a point on the real axis. Here real number line 0, 1, 2, sketch with me. Here real number line. Then here natural set now. Then integers. Then rational set. Now here the real set. then real but not rational, then this shaded region that belongs to irrational numbers. It belongs to irrational numbers. Natural, integer, rational, real, then shaded region, irrational. Irrational. Then here these point we have marked here integers, no? Then integers are discrete. Integers are discrete. But real mean here there are infinite real numbers within these 0 to 1, no? Then they are continuous. Real numbers are continuous, but integers, natural numbers are discrete. Discrete. Okay. So anyway, on this number line, when you select a point, then there will be a real number. There will be a real number, no? Then here there are few notations. Here positive real numbers. Here positive real number with 0 in non-negative. Negative. Real numbers. Here negative real numbers. Here non-positive. Real numbers. Non-positive. These are some notations. So when you are doing questions, we will see these type of notations under functions and many areas. Okay. Non-positive real numbers, no positive value. Positive real numbers, non-negative real numbers, negative real numbers, and non-positive real numbers. Okay. Now let's move further. Let's move a little further. See intervals. On real number line. Okay, write with me. Intervals. Here real number line. If we have A here, shaded greater than A. With here included, we call include. Here lower boundary a, upper boundary infinity. Then close you can denote by square bracket, and infinity always open. This is called open. Then left closed, left close. Then if you see this type of shaded region in number line, here this is not included. Then a upper infinity. Here open, infinity always open. That's how we denote using algebra. Then here a real number line, then this way shaded with include. Then upper a, lower minus infinity. Infinity always open. Here this is closed now. Real number line, here a, here not shaded. Then minus infinity lower, a open, open. Real number line, a, b, left right both open. This is not shaded. Lower a, upper b, both open. Real a, b, now shade both closed. A, B closed one denoted by square brackets. A, B, here A, B closed open. A, B closed open. Those are the intervals on the number line. So within this region, they represent many numbers. Continuous numbers it contains. No? Okay, just write. Yeah, this bracket closed. Here open. Close mean A is included. A is not included. Here A is not included. Infinity is always open because we don't know infinity now. That's why we take that one as always open interval. Infinity always open. Others can be closed or open. Closed mean included. Open mean excluded. Here, for especially this one, we say closed intervals. Here, open interval, closed interval, open interval. Here, left closed interval, left closed. The right closed interval. Right closed interval, left closed interval, then open interval. Okay. Open interval, closed interval, right closed interval, left closed interval. Okay. Now, let's do one another thing. I told you here a real number line 0, 1, 2, minus 1, minus 2. That is real number line. Then on this number line, when you select a point, then that represents a real number. No? Then half has special position. At the midpoint is half. Then 1/3 also segment, 3 segment, then here this will be 1/3. No? Then likewise, square root 2 has exact position. Okay, but square root 2 decimals are infinite. Still we don't know final decimal, but square root 2 has exact position on the number line. Square root 3 has exact position. No? Square root 5 has exact position. Let's see how to mark square root 2, square root 3, square root 5 on the number line. Okay. Here this is 1, exactly 1. Then half we can directly mark. Here half. Then 1/3. Set into 3 sections. Here 1/3. Likewise we can mark. No? Okay. Now you try to mark square root 2. You can get any construction. Okay, try it. 0, 1, 2, minus 1, minus 2. Okay, just think and do. I need exact position. First mark this one. Okay, I'll show square root 2, you do square root 3, 5 and 7. Huh? Okay, see this one. See this one. So you consider a square. Here 1 and 1, 1, sides 1. Then see diagonal. Then length of the diagonal 1 square plus 1 square root, no? That is root 2. Length of the diagonal root 2. Then root 2 mean we have exact value. Then here 1, no? Then same length you sketch perpendicular line here, same length. Then here length of this line will be exactly root 2, no? Exactly root 2. Then you may sketch a circle. Then here this will be plus root 2 and here this will be minus root 2. That's how we mark on the number line. Okay, do it. Okay, you think and do root 3, root 5, root 7. Root 3, root 5, root 7. Take little time. Now you know it's exactly root 2, no? From that you sketch another one line. Here 1. Here root 2 square, 1 square root. Here this length will be exactly root 3. Now you sketch a circle. Here this will be root 3 and this will be minus root 3. Then use square root 2 to get root 3 and you try to obtain root 5, root 7. Okay, then square root 5. Here 0, 1, 2. Minus 1, minus 2. Here 2, no? Take perpendicular length 1. Then 2 square plus 1 square root. Here this will be root 5. 2 square plus 1 square root. Now sketch a circle. Then here this point will be root 5, exactly root 5. And here this point will be exactly minus root 5. Then root 7 from here, square root 3, no? You sketch 2 line. Here 1, 2. Then root 3 square plus 2 square root. That is root 7. No? Here this will be root 7. Here from root 3, you sketch 2 line perpendicular. Then root 3 square 3, 2 square 4, 4 plus 3 7. Then root 7 here. Sketch a circle. Here root 7. Then here minus root 7. From square root 3, sketch 2 perpendicular line, length 2. Okay. Up to now we analyze about natural numbers, integers, rational numbers, irrational numbers, and real numbers, no? Real numbers. Rational numbers specialty, decimals can be finite or infinite. If it is infinite, it has recurring pattern. Irrational numbers is specialty, decimals surely infinite, no pattern like that, no? No recurring pattern. So when you consider decimals now, we have two cases. Finite decimals, finite. And infinite decimals. So for finite decimals means 0.1, 0.22, 0.154, then finite decimals are surely rational. That belongs to rational. Infinite decimals, we have two cases, recurring. Non-recurring. recurring and non-recurring. Then for recurring decimals, we say rational. For infinite decimals, non-recurring, we say irrational, no? Irrational. That's how we classify number. Then the number set here initially natural, integer, rational, real, here number set. Here natural, and here integer, here rational, here real. Here this is irrational, and here this part non-real, especially imaginary numbers, complex numbers. So we have discussed little things about imaginary numbers and complex numbers. Don't worry about that part. Later we will discuss this one under complex number lesson. Then no need to worry about that. But anyway, identify here the number set up to we know. Then non-real numbers already we have. Okay, as according to the algebraic operation, these numbers has evaluated. To define square root negative number, we have identified imaginary numbers. Okay, then real and unreal sum we define as complex. Real and non-real sum we say complex. Okay, then don't worry about that part. This is the thing that what we discussed up to now. Okay, you better to put that chart and here Venn diagram. Okay. Now further, we need to practice more questions. That's it. So one is rationalization of denominator. I'm not doing that today. Okay. Then contradiction method. Contradiction method. That's very special method. Not doing today. Then recurring decimals of fraction we have done up to some part. No? Then let's do few further questions. Recurring decimals of fraction part. Okay. Write down this. Express the following express the following recurring decimals to fraction. Express the following recurring decimals to fraction. Express the following recurring decimals to fraction. Okay. Now you do one by one. I'll give you small time. Question number 1. 0.8 dot. Do soon. Do soon. Don't write directly. I need that proper steps. Don't write directly. Need proper steps. 0.8 dot. Do soon. Eight or 9. Question number 2. 3.7 dot. Do soon. 3.7 dot. Do soon. Do alone. 3.7 dot. Do alone. 34/9. Question number 3. 1.75 dot. Do alone. I need your practice. Then do alone. 1.75 dot. 79 over 45. Zero point 002 dot 0.002 dot 0.002 dot 1 over 450. Question number 5. Two point zero one two dot 2.021 dot. Take time. One 1819 over 900. Two point three over 1.3 dot. 2.3 over 1.3 dot. Only dot here for 1.3. Take time. Twenty-three over 10, 1.3 dot 1 plus 3 over 9, 23 over 10 over 12 over 9. Then 9 goes to upstairs. Before that we can cancel now. Here 4, 3. 23 over 10, 4 over 3. Then 3 go to numerator. 23 times 3 and 10 go to denominator. 4 times 10. 69 over 40. 69 over 40. Here 2.3, 23 over 10, no recurring decimal. But here recurring decimal, 1 plus 3 over 9. 0.3 dot mean 3 over 9. So I took this one directly, but you better do that one separately and put it here again. .7 dot over 0.05 dot. 2.7 dot over 0.05 dot. Two alone. Two plus 7 over 9. Here 0.0 no? Get 1 over 10. 0.5 dot. 25 over 9. Here 1 over 10. 0.5 dot mean 5 over 9. Now simplify. Cancel 9. 5. Then 10 goes to numerator. 5 times 10, that is 50. Check it. 2.7 dot. 2 plus 0.7 dot. 2 plus 7 over 9. 18 plus 7, 25 over 9. then 2.7 dot 25 over 9. Then 0.05 dot 0.05 dot take 1 over 10, 0.5 dot 0.5 dot mean 5 over 9. Then 1 over 10, 5 over 9. Then we can cancel 9. You can cancel 5. Then numerator 5, denominator 10 goes to numerator. 5 times 10, 50. 50. Okay, identify the levels of fractions. 9 in here this level. Here this 9 in up level. Here upstairs. Identify the levels. Question number 8. 2.5 times 1.4 dot 1.03 dot 2.5 times 1.4 dot divide by 1.03 dot. Two point five, 25 over 10, 1.4 dot 1 plus 0.4 dot 1 plus 4 over 9, 13 over 9, 1.03 dot 1 plus 0.03 dot 1 plus 1 over 10 times 0.3 dot 1 over 10 times 3 over 9. Then 93 over 90. Here 90, no, 93 over 90. Then 2.5, 25 over 10. 1.4 dot 13 over 9. 0.1, 1.03 dot 93 over 90. Here 10, 9, 90 cancel. Then 25 times 10, 250, 325. here 1.03 dot 1 plus 0.03 dot. Then 0.03 dot we can take 1 over 10 outside, then 0.3 dot, then 0.3 dot, that is 3 over 9. No? Then 90 plus 3, 93 over 90. Two point five dot, 3.1 dot, 1.7 dot. Two point five dot, 2 plus 5 over 9, 23 over 9, 3.1 dot, 3 plus 1 over 9, 28 over 9, 1.7 dot, 1 plus 7 over 9, 16 over 9, then 23 over 9, 28 over 9, here 16 over 9, cancel 9, then 16 divisible by 4, no? Here 4, and here 7. Then 23 times 7 in numerator and 9 times 4 in denominator. (161 over 36). Okay, question number 10. 1.52 bar. 1.52 bar. If you can write directly, you can do. If you can write directly, you can do. Zero 0.52 bar. 1 plus 52 over 99. 151 over 99. 151 over 99. 2.71 bar. 2.71 bar. 269 over 99. 1.215 bar. 1.215 bar. Bar for 15 only. For 401 over 330. Simplest one. Okay, now so far we identified the things about numbers. So we have to do more practices on the irrational things, irrational numbers, and again we have to practice about contradiction method. Okay, then this is the things about numbers. So for your first term test, definitely you will get recurring decimal fraction part and rationalization of denominator. Rationalization of denominator very important. So when you are doing questions in A level examination also, you will get irrational expression simplifications. Okay, then that's all about numbers. That's all about numbers. Okay, then that's all for today. Then next week we can do more things about numbers and functions. Okay, then see you next week.